Good morning, good night, whatever. Today we are doing chapter 4 of the course textbook, Logic for Computer Science, Classical and Non-Classical, Springer, 2019, and I am the author. So we go to chapter 4. Chapter 4 is about general proof systems, syntax and semantics. So it really explains the relationship between the syntax and semantics. And here is the plan. There are 6 parts. We will go pretty fast because there's a book and there are slides to be read. And set 1 is introduction. And then there are definition of syntax. And we will talk about syntactic decidability and consequence operation and about non-monotonic reasoning, which is important part of artificial intelligence. And then slide set 2, we'll talk about it later. So slide 1, introduction. So what is a proof system? Proof systems are built to prove. It means how to construct a formal proof. It's not like proving in your head. We'll talk about formal proofs of statements formulated in a given language. So the first component of a proof system is a formal language L. Proof systems are inference machines with statements called provable statements being their final products. And we start as it is like inference machines, so we start with I'll show you the picture. We start with axioms, then we apply to the axioms rules of inference, and then we apply rules to we apply rules. See, we can show here. We always would start with axioms, and now the inference machine applies the rules. So rules will define what are axioms, we define what are the rules and how we apply it. And the whole process is called a formal proof in a formal proof system. And then provable formulas, it means theorems of the proof system. Now, rules of inference, which we are going to define formally, of a proof system have to preserve truthfulness of what they are going to prove, because of not why to prove if you don't know that what you prove at the end is true. The notion of truthfulness is always defined by a given semantics M. We talked about semantics in the previous lectures. Rules of inference that preserve truthfulness are called sound rules. So sound rule is a new, so truthfulness, semantics, sound rules under given semantics. And we say that rules are sound under one semantics and can be not sound under another semantics, and we will see the examples. So our goal first, when developing a proof system, is to prove the following theorem. And this is called Soundness theorem. And here we have Soundness theorem for any formula A of the language of the system. That's very important, because everything, when we do formal proofs, everything has to happen in the language of the system. If a formula is provable, whatever it is, and we'll define it formally, from logical axioms LA of the system only, then A is tautology under semantics M. So that is general formulation of soundness theorem. By definition of the notion of soundness is connected with the given semantics. And you will see that some systems proof system can be sound under one semantics and not sound under other semantics. Of course, when you do mathematics and you do things in your head, whatever you are, and you do proving, the proofs are not formal proofs, and everything happens under classical semantics. If your semantics is well sorted in your head, your proofs are correct. It means true. So, for example, a set of axioms and rules sound under classical semantics might not be sound under Lukasiewicz semantics, which we covered, or many other semantics. Now, we have certain notations because we built a formal framework. We denote by TM the set of tautology defined by semantics M. That's how we did in previous chapter. So TM is the set of formulas of the language, F is language of the system, which are tautologies. This is a symbol, tautology under semantics A. So when we have tautologies, because semantics is defined by the set of tautologies, we have a natural question. Are all tautologies, it means all formulas which belong to a tautology, provable in the proof system? We know in a sound system, we know if you have a proof, you know that it's a tautology. But the inverse question is that. Can we prove all tautologies? And positive answer to this question is called completeness property of the system S. And we have, so when you build the proof system for any logic or for any theory, if you know that your proof system is sound under your semantics, our second goal is to prove the theorem, which is called completeness theorem. And completeness theorem says, and we will be spending rest of our course on proving completeness theorem for different proof systems under different semantics and developing different techniques to prove the theorem. That's why we talk about it already now. For any formula of the language, we say that A is provable in S if and only if A is a tautology, and symbolically that is a symbol. A has a proof in the system S, and completeness theorem says that A has a proof if and only if, and that is a symbol that A is a tautology of the semantics M. Completeness theorem is composed of two parts. One is the soundness part. It means soundness theorem, and the completeness part that proves the completeness property of the sound proof system. Also, proving the soundness theorem under given semantics is pretty straightforward. So it's not difficult to prove, and I will show you how you prove and what are the steps to prove the soundness theorem. So how you do, first we prove that all logical axioms are tautologies, and then we prove the inference rules, which we are going to define, of the system preserve the notion of the truth, so then whatever you prove is also a tautology. Proving completeness is a very, very difficult task. It's crucial and often just impossible. So, and there are different techniques to prove it, and that is a really deep, deep subject. So we studied two proofs of completeness theorem for classical propositional logic in chapter 5. We start with, again, like with syntax, like with semantics, with propositional languages because they are easier to understand. Then we will do it in predicate logic. I'll discuss in chapter 8, 9, 10, and 11. And so once you understand how things work and easier techniques for propositional case, you will better understand what happens in more complex predicate logic cases. So syntax. Now, that was just intuitive introduction. And now we go into serious stuff. So it means definition. So, and as I said, when defining proof, we specify the formal language. Now, of course, language is alphabet and formulas, well-formed formulas. Now, in many proof systems have used not only formulas as a basic expressions, especially all automated theorem proving systems use more than formulas. That's why we will take as extend the notion of formula of a language to a set of expressions. Sometimes we add some additional symbols. And of course, we have inference rules. The inference machine is defined by setting as a starting point a certain non-empty subset of expression of logical axioms, LA, and production of probable statement is done by the inference rules. And now we have an inference rule. Remember, the inference rules do not carry any meaning. They just change certain formulas or set of formulas or sequences of formulas into another formula. This is why when we investigate proof system, its investigation of a proof system is called syntax or syntactic investigation as opposed to semantical methods. So now we talk about only just symbols and how we change one set of symbols into others following certain rules. Of course, syntax semantics connection within a proof system is established by Soundness and Completeness, and then we'll discuss it later. And here's the definition of proof system. You can see it's a very formally, to define a proof system, you have 1, 2, 3, 4 pieces. A quadruple, it's called quadruple, where, and I am going to write it on the blackboard so we can here. S, and I will keep it, is language, expressions, which you think the formulas. We have logical axioms and rules. Language, very important. Everything always happens within a given language. This is expression of the language. These are axioms, but they are called logical axioms because we want them to be tautology when we talk about semantics. And then these are axioms, and they are rules of inference. So, and we assume that all the sets, logical axiom is finite, finite subset of expressions. Rules are finite number of rules. So we talk about there's everything is finite. You can generally define infinite number of rules, infinite number of axioms, but it's theoretical. We don't want it. And the language, of course, language is, as we know, is a tuple, alphabet, and a set of formulas. And of course, we assume that A and F are enumerable languages. So we talk about in both propositional and first order languages, they are all enumerable, so we talk about enumerable languages. Expressions are, as I said, we can, from formulas, we can, for different proof systems, we can form different expressions. Like, for example, in automated theorem proving system, usually we use as the basic components set of special expressions. In chapter 6 and 10, we consider finite sequences of formulas, the basic expressions. We also present proof system with use of another kind of expressions, which are called Gentzen sequence, which have additional symbols. And some other system use other expressions like clauses, set of clauses, sets of formulas. So that's why in the definition of a proof system, we have here expressions, not only formulas, in many cases, and we start in cases where the expressions are just formulas of the language. So now we go logical axioms. We distinguish a non-empty subset of the set of expressions, which we call logical axioms. And we assume that's a finite set. Of course, we have the semantic and the rules of inference. We assume that as I said, we assume that we have a finite number of rules of inference. And also we assume that we can effectively decide for any inference rule whether a given string of expression form premises and conclusion or not. And what is a rule of inference? Here is rule of inference is a relation. It's a relation which takes e to the power m is m premises, is a tuple which takes m pieces, p1, p2, pm, and returns 1, which is called a conclusion. That's why we use the num c to say conclusions. P1, pm are called premises of the rule of the system, and c conclusion. That's why we usually write premises as p for premises and c for a conclusion. And here, you know, we write those rules not in a fancy way as relation. It's important to say that rules are relations. Rules are relations. They don't need to be function. Because when you solve the rule of inference, you always think about them as a function. Takes two, for example, premises and returns conclusion. But if there's only, for two premises, if there's only one conclusion, it is a function. In general, rules of inference can be relations. It means for two premises, you can have different conclusions and different possibilities. And we will use that notation for rules of inference because everybody, we are used to that. And the finite product of single or multiple use of inference rule of the system with axioms taken as starting point are called probable expression in the proof. And now we have to define formally what does it mean. So we call that the single use of inference rule is called a direct consequence. New word, single use of inference rule is called a direct consequence. And multiple application of rules of inference with axiom taking at starting point is called a proof. What does it mean that multiple application? That would be a formal definition of formal proof. So, for example, direct consequence for a rule, if you have a rule, conclusion is called the direct consequence of its premises by the virtue of a rule of inference. And now we have a definition of formal proof. And that is the first basic definition which Yeah, which we are going to work and explain what it means. So formal is, when you do proving, you like have in your head, oh, I do this, and I do this, and then I apply that, and then I got whatever, and finally 2 plus 2 equal 4. I proved 2 plus 2 equal 4. Now we are talking about formal proofs. It's not formal proof as opposite to what intuitively we use as the word proof is the following. Formal proof is a sequence. So to have a formal proof of course, in S is a sequence A1, A2, A3, AN, n greater equal 1 of expression such that the first you start is axiom. So it means A1 it belongs to our chosen set of axioms. Now, we prove something. So formal proof in S of certain expression of E, because we prove E in a system S. So the last one, we end, start, end is what we prove. And in between, it means I greater for I greater equal 1 less equal n, AI is axiom. So it means you can always put in an axiom, or we get it. I'm not being very scientific, by application of a rule of inference. But application of rule of inference where all premises are, so you have a rule of inference and all premises, when you have AI here, all premises must be located before. So AI is conclusion of that rule of inference, and premises must be before, so you construct such a sequence. So and n is the length of the proof. And of course we have notation, is that we write, we write this, so it means E has a proof. This is a symbol for a proof, formal proof. In S, that is our notation. And now you have P, fat PS is the set of all expression which have a proof in the system S. So they are called probable expressions. So now let's see, do a nice little example. I'm going to write this example on the blackboard. Now, let's look. We have two proof systems. I want to define a proof system. OK, I want to have a simple proof system. So I say S1. So what does it mean? I have to say what is the language. So I have a language which has only implication. very nice little language. So formulas has only one two-argument connective, which is implication. I have expression are just formulas of the language. And now I take logical axiom. I have to define. I say I have logical axiom. It has to be set. So I have logical axiom is a set which has only one axiom, which is a formula A implies A. Remember that logical axioms is subset of formulas. That's why we put wigglies here. That is one element axiom. We can write it A1 is A implies A. We have one axiom. So this is set of logical axioms. Rules, we have to define the set of rules. We have only one rule. Oh, I have language. Wait, let's do the language. I have two connectives, P and implication, where P is one argument connective. You can PA reads, for example, probable A. Whatever. It's your symbol for whatever you want to read, and implication is two-argument connective. So, and I have one rule of inference, which says that if one argument, if I have a formula, I want to have, wait. If I have, you see, here I have one rule of inference. If I have a formula B, I can write PB. So this is a premise. This is conclusion. There's one premise and one conclusion. So it's one premise rule. And I have a very simple system. Now, I have also system 2, which looks very much like this one. The language is the same. You have the language is exactly the same. The only thing I change, I write A implies A, and the same rule of inference. So the same R. So we have now two proof systems. I defined you two proof systems. What is the difference? But they have exact, and of course here, what you say, B is any formula. So it means that if I have already B, I can write PB. So let's see how you construct a proof. Construct a proof, formal proof. What does it mean? You have to start with axiom. So for example, I write C implies C. Capital C. So this is my, in the sequence is A1, and this is an axiom, because AB, here, A, B, A is any formula, so I call this formula C. I start with C. Now, what the rule of inference says, that if I have a formula, so that is my formula B, I can apply this rule and write P in front. So my second step in a formal proof would be P, C implies C. And I can say, OK, I end here. So this is proof of, in our S1, C implies C of length 1, 2. So I proved P, C, and C. So I can write in S1, I proved C implies C. Of course, in S1, I also can stop. You can stop your proof here because, and I can say that in S1, I proved C implies C. But also, I can continue my proof. I can again, for example, write H3. In the proof, I can again put axiom. So I put A implies A. And this is axiom. So I prove now 1, 2, 3. I proved A implies A. But then I can keep going, and I can write PA implies A. And application of the rule, now this is our B. So that those symbols, that's what they mean. They mean that A and B and C are any formula, so you can put under that B, under this B, I put this. Or under this B, I can put that as my B. And also, if I want to use the rule to this, I can write another element of my proof. I can use P of C implies C, you see. So, and this is a proof of the length 5 of PCC, because when you prove, you can pick up, when I am in the moment of the proof, I can apply to anything which I have already. So in this moment, I use this, and I apply the rule. And here I use that, and I apply the rule, and so on. So, and that's how we form the formal proof. It's just, you think about it like, you have like nice symbols, and the rule says how you rewrite symbols by different symbols. Now let's look which is the difference between those two systems. Is there any difference between S1 and S2? For example, can you prove B implies BP in S2? A second for thinking. Of course, I wouldn't have asked if the answer was yes. The answer is no, and that I gave you this example to make sure that you still remember the difference of notation. So here I'm going back with notation of formulas. We denote A, B, C, A1, A2, small letters are variables, propositional variables. And we know that variables are formulas. They are called atomic formulas. And if I have already two formulas, this is a definition, we can write PA is a formula and A implies B is formulas. It means, and this is recursive definition, it means capital letters denote complex formulas. Small letters denote only variables. So, of course, you cannot write, if I write capital letter, so that is not logical axiom of S2, because B, for example, can be A implies B, P implies C, can be such a complex formula where you only axiom can be variable implies variable. So you prove different things from that in this system, that for this is much richer system. So that I gave you those definitions on the slides, just to remind you of that. And I say, observe that the system S2 has also only one axiom, similar to the axiom of S1, and they have the same rule of inference. For example, that complex formula, this is axiom of S1 because this is capital A. You see that this is the same formula as here, and it's not an axiom of S2, which is S2 is only A implies A. You can only have one variable, and here you have a complex variables. So that is very important to remember when you construct the formal proofs. And for example, in system S1, you can have this complex formula and then you can apply the rule. So you can apply, if you have this is your axiom, and in S1, you can also take as a capital A, is in particular a small a, so that was all formulas which you can prove in S1, and you can put it as S2, because in S2 that is also logical axiom, and this is not logical axiom of S2. And here you have some example of formal proofs, and you can see, and then how we will be writing the formal proofs. Like, for example, formal proof of P, A implies A, is the same in both systems, because this is an axiom, which is axiom in S1 and in S2. And then you apply the rule for B equal this, and you have application. Now, the same, if you start with this, we prove P A implies A, and these are the same proofs in both systems. Now, let's take a more complex system. And I'm not going to go through all those examples. They are in lecture notes, and they're in the book, plenty of examples. But I just want to show how you build the proofs. So now the proof system has still the first axiom. Now, you see, we write the proof system. The expression are formulas. Now, this is logical axioms. You have two axioms. One is A implies A, and comma, second. So you have two axioms. A implies whatever is the formula. And you have one rule of inference, which says, if I have a formula A implies B, I can write a formula B implies A implies B. And again, remember, I have R is A implies B, and structure of the rule says that I can apply A implies B. And A, B are any formulas. And now the language, you see, now the language is different, has negation and implication. So formulas are from that language. That's what I had an axiom. Axiom 1 was A implies A, and axiom 2 had negation A implies not A implies B. Languages with negation A and B are any formulas. And the rule says that if I have, so let's do example of the proof. I write, first must be an axiom. So I write A implies not A implies A implies not B. Nice formula. Is this an axiom? Spy with your little eye. Axiom has a formula, and here you have implication, so that is your formula A. Now, it says that you have negation of A. Yes, that is a negation of A. And implies, this implies, that implies, and that is your B. So, yes, it is an axiom, so I can put it as a first step in our proof. So, now, what the rule says, the rule of inference says that if you have already axiom, so that is correct, this is an axiom. The rule says if I have implication is main connective, so that is your main connective. So that is for the rule, this is A, and that D in that is the whole B. So the rule says if I have A implies B, I can write as second conclusion would be what? B. So B is the whole thing, so you write not A implies A. This is, you write the whole B. I'm taking care. So this is my B, that B. Now I can write implies. And here I can write formula A. This is your A implies, and again the whole B. Not A implies not B. And you can see I proved such a complex formula by that rule of inference. Again, it's a little bit more complicated example, but that is the whole, that's what the proof means. Here you have another proof, which I start with the axiom A implies A. I use exactly the same. And then, now, when you look at this, in the rule of inference, A is A and B is B. So it means that I can write A, B is A, so I can write A, and now A implies B is A implies B. And again, you can apply the rule to this, and you have a proof of A implies A, blah, 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 blah. So that's how you construct the proofs. And now, nice exercise. You have two rules of inference. And that, you see, all these examples I gave you, there was one rule of inference with one premise. Now, what happens when you have, for example, rule of inference with two premises? When you have two premises, what you need to do, if you want to, now you have the rule of inference with two premises, whatever is the language. So now we have a, I have to see if I have the proof here. Ah, no, so you see, that's why you need me writing on the blackboard to show you how to construct the proof when you have a proof system with two premises. So let's do it together. Oh, it's very, oh, maybe I'll put it here so I'm not running back and forth. So now we have two rules of inference. Now we have the language to change from implication. P is one argument connective, and you have axioms, which is A implies A, just to make it simple. This is logical axiom. And you have two rules of inference. One says that if I have B, as we had before, I can write PB, and the second one has two premises, which says if I have already A, B, one premise, second, I can write P, A implies B. So let's see a small proof. You see, okay, to start, I write axiom. So let's write axiom. I like small letters. A implies A is axiom because capital A can be a small a. Formula A implies A. Now, if I want to apply rule 1, I apply rule 1 to this. Now, the B in the rule is this. So I write P, A implies A. So I proved P implies A like we did before in S1. Now I have already two formulas, you see. So I can apply two-argument rule. So now, for example, I can say that I call this to apply. What does it mean to apply this rule? These premises of the rule have to be in my sequence already created before the application. So I write P, A implies A, implies A implies A, and I write P in front. Ha. Question. Is it a correct step? Silence. Yes, it is a correct step. Why? Because by definition, to apply the rule, the premises have to be located before. It doesn't say which order. So I take as A here in the rule, I take this, and I take this as B. Both A and B are already in our sequence. So now I can write P, this is P, apply to A implies B. This is a correct proof of A implies B, and so on. So first, you remember that when you construct the proof, you can pick up the order is not, for example, now I can keep going. I can write A4, and I write I write P, A implies A, for example, implies that I took this as A, and I take this as B. That would be too much writing, right? 8-3. You see, I can write here. And that is a proof. Now I took this as A, and this whole thing, A3, as B, and I write P in front, A implies the B, which is the whole P. So the proofs get very complicated. Okay, the next important subject is syntactic decidability, because it's very important for automated theorem proving. So let's think about decidability in general sense. For any proof system, we assume that two properties, we already did assume those properties, and now I'm going to do this. First, that we can always decide for any expression, we effectively can decide whether the expression is an axiom or not, because that was our assumption about the system. And for any inference rule, we can also effectively decide whether the strings of expression form premises or conclusion. So that is that we can recognize what we have already. And also, the fact that we have those two properties does not mean that the statement E is probable can be effectively decided. Here, we can effectively decide because look how nicely I construct. Of course, if I give you this huge expression and ask you, can you find the proof? Can you find the proof automatically? That is what we are going to decide. When, if I give you, for example, such expression or such a long expression in given proof system, I can ask, can you find the proof? Can you find it automatically? How you find the proof? So that is another notion of decidability. So we say the proof system in which there is an effective decision procedure for determining for any expression whether there is no proof is called no proof is called decidable. So this is only not finding the proof, but you can somehow can you decide there is a proof or not a proof. But this decidability does not require to find the proof. It just requires some decision. For example, when you take propositional tautologies, you know that I have a tautology, and I can semantically decide if that formula is tautology or not. And now I have a complete proof system for classical logic. So I have a tautology. Completeness means tautology if and only if there is a proof. I know that is a tautology. I have a completeness. So is the decidable system. But I don't know how to find the proof. So that is general decidability. And now we say that we want to find the proof. Here I said, okay, I give you formula. Can you find the proof automatically? And that is called a proof is syntactically decidable. So we say the proof system for which there is an effective mechanical procedure that finds, it means generates a formal proof of an expression, if it exists, is called syntactically semi-decidable. If exists, it's called semi-decidable. If exist or not exist, it's called decidable. Decidable is stronger than syntactically decidable. So that is one of the first and the basic problems of mathematics. David Hilbert, at the turn of 20th century, posed 20 problems for 20th century, which was called the Hilbert program. And there is one problem left, so we are pretty lucky on 22nd. But one of the main goals of the Hilbert program was to provide secure foundation of mathematics. And in particular, one of the first problems he stated was the problem of decidability. It stated that there should be an algorithm of decided the truth or falsify of any mathematical statement. And it must be done by finitistic methods. Finding the proof is a finitistic method. And Kurt Gödel proved in 1931 that most of the goals of Hilbert program were impossible to achieve concerning foundation of mathematics. But 34 years later, Gerhard Gentzen, in his work published in 34-35, gave a positive answer of the possibility of existence of syntactic decidability. He invented the proof system for classical and intuitionistic logic, which are called Gentzen type formalization, and proved syntactical decidability, not defined the way we define now in modern language, for propositional part of both logics. And we will study the whole Gentzen type formalization, chapter 6, 7, and 10. This is very important part. Okay, and that is automatic theorem proving. We are going to show, we were going to show from completeness theorem proved in chapter 5 and the decidability of notion of classical tautology we prove in chapter 3. And Gentzen proof systems for classical and intuitionistic propositional logic we present in chapter 7. And now we have different simple proof systems. I'm not going to, I show you a lot of that already on the blackboard, but, and in general, the syntactically decidable proof system is such that we have a procedure. How this procedure works, first, we check for our propositional systems. Check the main connective. If the main connective is whatever the rule says, it means that A was obtained by the given rule, because that was for our system, this system. B rule was B you conclude PB. And so what does it mean? If you want, you have a rule like this. If you want to search for proof, I have this. So the rule says I can erase P. And I can go back. You see here, our rule says for this, if it's, I can erase P. Here, you have A and B. So if you have P and you have this, you can know what is A and what is B. So here you know that A is there, I have, and B is this. You can parse it and see. So you can go back and write this and write that, and so on. So you can recreate the proof. So you can have a procedure which would find the proof. Chapter 4, the last two parts. Part 5, we are going to talk about semantics. The chapter is General Proof System, Syntax, and Semantics. So now we do the semantics. And we'll talk about soundness and completeness notion and how you prove it and what does it mean. And part 6, just few exercises and examples. So semantics. Now we define formally semantics for a given proof system by specifying the semantic links to all its components as follows. So first semantic link, language. The language of the system can be propositional or predicate, and we denote by M a semantics for the language M. This is our standard notation, and we called M for short as semantics for the proof system. Now, in general framework, M can be classical or non-classical semantics, also can be propositional or predicate depending on the language and the nature of the system, and also can be extensional or non-extensional, as we covered all this in chapter 3. So we use M now as a general symbol for a semantics. And of course, the system has the set of expression, not only formulas. So we always have to extend a given semantics M to the language of the system, to the set E of expression of S. Sometimes, like in the case of resolution-based proof, we also have to prove a semantical or semantic equivalency of new created expressions E. In the case of resolution, that would be set of clauses with appropriate formulas of L. For example, we will talk about automated theorem proving, RS, in chapter 6. The basic expressions of that proof system based on the language, our standard language with conjunction, disjunction, negation, and implication, and we extend that classical semantics to the set F star of all finite sequences of formulas. And that is, like we say, we extend V. V is a variable into TF, and now delta is a finite sequence of formulas, A1, AN are formulas, and we say we extend V to V star to all the set of sequences, taking that this comma becomes the disjunction. And in shortcut notation, we write delta equal A1 union or disjunction all the formulas. So the extension of comma in a sequence is disjunction. Semantic links 3, we have to define logical axioms. So given a semantics M for the language, an extension now, we extend the notion of tautology to the set of expressions. So we have to say expression E in E is a tautology under the semantics M, and then in normal way. And now we denote as Tm, fat Tm, as the set of tautologies under semantics M. And of course, for the logical axioms, we always take a subset of expressions, and we want logical axioms to be tautologies under the semantics M. So LA is subset of tautologies. Now we have a rule of inference, and we want the rule of inference to be sound. So the word is sound under the semantics. So you have, if we have a rule inference with premises P1, Pm, and conclusion C, we say that such rule of inference is sound under the semantics M if and only if all models, M models of the set of premises are also M models for the conclusion. So in propositional case, and this is a general definition, whatever is the model, and in propositional language and extensional semantics, models are defined in terms of truth assignment, and we say that M, the rule is a sound rule under semantics M if and only if you have for any V truth assignment, if V is a model of all premises, then it's a model of the conclusion, of the set of premises. So then we can rewrite it from the definition. What does it mean that something is a model of a set of expression? We write that it means that V is a model, I just remind you, that V is a model of a set of premises. It means that V of all premises is true. So V is a model for each of the premises, then is model of conclusion. So we can say that that's what we always say, that rule is sound. If all premises are true, then conclusion must be true. So, for example, we have a little proof system of the language negation, disjunction, implication, and with two rules of your inference. One premises rule. And you can very easily see that is sound under H semantics. It means that the rule with M in, we have a V which takes variables. Now in H semantics we had F unknown true, and we assume that V star of A implies B is true, and you have to show in H semantics that V star of B of A implies B is, this formula is also true. So V is a model of A implies B, and we have to, this is V, and that is a formula, needs to have those brackets. So V is a model. If V is a model now under semantic H of A and B, then V is a model under semantic H, and you have H semantics of B and A implies B. And this is very simple exercise which we did already in chapter 3 many times. And also you can do the same in this, and the same. So this is for the rule 1. This is for rule 1. And for rule 2, in the rule 2, we have that rule 2 says that double negation A. So really, if V is a model at the HL of double negation, then V is a model HL of A, and this is by simple verification. That's why we played with those semantics in chapter 3. And it's not sound at the H semantics because of that. You see, at the H semantics, you have that this is not true. And again, why? Because you take a V, let's say V. This is not true for HA semantics. So that's why we did all those tautologies and all those models for different semantics. And and you do it by verification, and of course everything is sound at the both are sound at the classical semantics. So now we introduce a very important notion for the part of automatic theorem proving. And the system will consider for automatic theorem proving. That is a notion a little bit stronger than a notion of soundness of the system. So we say that rule is strongly sound under given semantics if and only if the condition is not if then, but is if and only if. So in a sense, you say that all premises are true, or conjunction of all premises is true under semantic sum, if and only if the conclusion is not true. For example, you have modus ponens rule under classical semantics. Let's see it. So not all under classical semantics, for example, you can say that you have a rule A, B, and you do not A and B, not A, not A, or not B. You have such a rule. You can see why I was thinking about this rule. It is strongly sound under classical semantics. Why? Because you know that A and B in classical semantics is logically equivalent by double negation and De Morgan law, not A or not B. And I'm checking in my mind, is it true? Because that is not by De Morgan law, not A and not B, right? We know that by De Morgan law and double negation, you get this is A and B. So this inference rule is strongly sound because A and B is logically equivalent to the conclusion. So strongly sound if you have rule which has N and has a conclusion, you say that is strongly sound loosely, not very, this is a fancy way to say, but what does it mean? That if conjunction of all premises is logically equivalent to the conclusion, the rule is this only. V is a model for all. It corresponds to the fact the conjunction of all premises is if and only if means is logically equivalent to the conclusion. So, and so we have a strongly sound rules, but one of the basic rules in logic is modus ponens rule. A implies B. We conclude B. This is modus ponens. That is sound. And not strongly sound. Why? Sound is very, I'm doing an exercise. So what does it mean? Sounds that we have in shorthand notation means that A is true and A, B is evaluated into T. This is a shorthand notation. Instead of writing V star of A equal T, we can write shorthand notation for any V. So what we have to evaluate the value of B. So what does it mean? A is true. A implies B is true. That is only if and only if, by definition of our implication, just to remind, TF, TF is false and true in all other cases. So this is true when A is true. So it means true implies B is true by definition of implication, if and only if B is true. So that is proof of soundness of modus ponens. Now, it's not strongly sound, and because A and A implies B is not logically equivalent to B, give nice exercise. So that is to remember. All right, so the strong soundness we defined for given formally, given a proof system, we have two conditions. The system is strongly sound if logical axioms are tautologies, and the semantics, and everything is relative to the semantics, and each rule of interest is sound under semantics. So so it means the condition also that condition C2, you can say that each rule of inference is strongly sound under semantics too. So you have sound, and for strongly sound, that was the soundness. For the strong soundness, you replace this condition by strongly sound. Sound, strongly sound. Now, of course, remember that that is a nice example to this rule we just proved. You did prove that this rule is strongly sound under H semantics. So it's sound. It's a sound, but it's not strongly sound because that is not logically equivalent to that under L semantics, and is not sound under H semantics because you have to check the axioms. For example, logical axioms under L semantics, the axiom, the both axioms are classical tautology, and the first axiom is not L tautology. So the first axiom was not A, not A implies A is not L tautology. Why? Because if you have V variables into t unknown false, you get shorthand notation, and you say v a is unknown, you get not unknown, which implies unknown. In L semantics, you would have that negation of unknown is unknown, so that would be negation of unknown implies unknown, and negation of unknown is unknown implies unknown, which is unknown. So that is in L semantics. You get that this is not a tautology in N semantics, because that is a contra-model for that formula in L semantics. That was a little review of chapter 3. And the other one you can check how it looks like. So when we develop a proof system and its semantics M, the first goal is to make sure that if the proof system is a sound, that means it has the property stating that if we prove S is, if all we prove in the system S is always true with respect of the given semantics. And that we formulate it in the form of Soundness theorem, which says that let's P S would be all probable expressions in the system S, and Tm is tautologies under semantics, and the Soundness theorem says that Ps is included in tautologies under semantics. And from the inclusion of sets, it means that if formula expression belongs to PS, it means if has a proof in S, then is a tautology under semantics. And of course, we prove it. If how you prove the soundness, you have to prove two conditions. It means you prove that logical axioms are tautologies and all the rules are sound. So by the induction over the length of the proof, you get that if has a proof, then is a tautology. So now the question is, so we have a sound proof system. It means anything we prove in the system is true under given semantics. Can S prove all statements we know to be tautologies with respect of its semantics? And that is called completeness theorem. So completeness theorem says that given a proof system and the semantics, that PS, everything which is provable, is a tautology, and any tautology has a proof. And completeness theorem, and that will be always our goal if you create a proof system and create semantics. The goal is to prove soundness and completeness if you can, and we will be spending a lot of time proving completeness theorem for different proof systems, for different semantics. So, and another thing, completeness theorems consist of two parts: soundness part, which is implication, and completeness. This is called the completeness implication. So the completeness implication, any tautology then has a proof. So that is our so now proving and disapproving soundness theorem for system is straightforward, right? You take the axioms, you show if they are sound, you show the soundness or strong soundness of rules of inference. That is, and you have find a number of them, so that is easy. It may be a little bit of semantics is complicated, but it is straightforward. But the completeness part, that all tautologies have a proof is crucial and difficult. And there are many methods and techniques of doing so, even for classical proof system. Non-classical logic usually require new, sometimes quite very sophisticated methods. So we present two proofs of completeness theorem for propositional Hilbert-style proof system for classical propositional logic in chapter 5. So that would be our next chapter and next lecture. We present constructive proofs of automated theorem proving system for classical propositional logic in chapter 6. We discuss the proofs of completeness theorem for intuitionistic and modal logic in chapter 7, and we provide proofs of completeness theorem for classical predicate logic in chapter 9 in Hilbert style, and in chapter 10 for Gentzen style, which are automated theorem proving systems. So we already did nice exercises and examples. Here you have one by one. There's plenty exercises and examples in the chapter. And there's a nice solution for each example. And here is exercise which I leave you with. We have a proof system with two rules of inference. And we have language, implication, disjunction, conjunction, and verify if it's sound, not sound, and the classical semantics. Remember, there are two a rule with two premises, and find a formal proof. We were doing the formal proofs some time ago, and show that of a formula, of that formula is show that it means that we have a formal proof in that formula, and does it prove that if you found a formal proof, does it prove that it is a tautology? And of course, when you look at my questions, by now you should know that if I say, does it prove that something, it means that probably that is not true. And why it might not be true? You found the proof very easily. Why that would not be true when the system is not sound. So you can write the formal proofs, but if you do it in the system which is not sound, you prove something, but that is not a tautology. This is the case in this example, and I will leave you with that.